Hi dear students, in this presentation we will be discussing about threshold for creep and different preventive measures for the creep, as well as we will be discussing another concept, that is what is called super alloy. Okay, so coming to the first topic, that is threshold for the creep. In this figure you can see, as I have already told, creep is directly depending on the stress and temperature. So while drawing the creep curve, we are keeping the stress and temperature constant. So it is possible to draw the creep curve for different constant stress and temperature. So here in this graph, it is shown that creep curves for a particular material at different stress and temperatures are shown on a single curve itself, single graph itself. Okay, so you can see here the temperature is less than zero point 0.4 melting temperature of the particular material. So the temperature is less than 0.4 Tm. That is what is the meaning, and this curve shows the creep curve for a temperature less than 0.4 Tm, and this one is for a particular stress and temperature combination. Constant stress during this stress curve is sigma 1 and temperature is T1. For this curve, the constant stress is sigma 2 and temperature is T2. Here it is sigma 3 and T3. So different set of sigma and temperature, stress and temperature combinations, uh, corresponding creep curve is shown here. Of course, T1 is less than T2 and T3 is always greater than T2, like that. See, T3 is greater than T2 and T2 is greater than T1. Similarly, sigma 3 is greater than sigma 2 and sigma 2 is greater than sigma 1. So coming towards this side, stress and temperature is less, and going upward, stress and temperature is more. Okay, so you can see from this figure, you see if the temperature of the material is less than 0.4 times Tm, there is no much creep is we can see that there is not much creep is happening, because at low temperatures the most of the mechanism which is leading to the creep is not present there. Only mechanism which will lead to the creep at low temperature or at room temperature, mostly at room temperature, is because of that screw dislocation, and all other requires higher temperatures. So at low temperature the creep formation will be much lesser, and if you increase the temperature, of course all other deformation mechanism will come into picture, and this will cause for the greater creep. That means more deformation or straining rate will be much more, and finally the rupture or fracture will take place. This crossed symbol shows the rupture point. From this figure you can see that if the for a particular time, if the temperature, see I am drawing a vertical line here for a constant temperature, the strain rate, you can see it is gradually increasing with respect to temperature as well as this stress. Okay, here this curve is having almost zero strain rate or slope of this curve. Since this line is horizontal, slope of this curve we can say it is zero. Slope of the creep curve is actually delta E, that is delta strain divided by delta T. So here with respect to temperature there is no straining, for whatever may be the time, there is no straining, but here you can see slight increase in slope is there. Here slope of the curve is much more higher, that means straining rate with respect to temperature, increase in temperature will be much higher here. But here the most here compared to this blue curve, here we have a higher strain rate with respect to change in temperature. That is what is the meaning of this one. So now our aim is to define what is threshold for the creep. Both temperature and applied stress influence the creep behavior. That already we have seen. See, as the temperature and stress is increasing, creep curve. See, the fracture point is becoming at lesser time, within less time interval, fracture will take place. See, if the temperature is very low, it will not fracture at all. If the temperature is at this range, that is T1 and sigma 1 is the combination of stress and temperature, then the material will withstand that same stress for a long time. But if you go towards this side, what happens if temperature and stress is increased, means within a short period of time the failure will take place. This point, this cross point 1 2 3, all these points represents the fracture point. Okay, so both temperature and applied stress influence the creep behavior. Figure shows that below 0.4 Tm means melting temperature in Kelvin, the creep strain is independent of the time. See, with respect to time, there is no change, there is no further straining with respect to temperature in case of Tm less than 0.44. With increasing stress or temperature, the following will happen. If we increase stress or temperature, if you increase, the same thing is happening. So that is, if you go upward, these things are happening. First one is instantaneous strain increases. So you can see in all these curves, strain rate is increasing. Here strain rate is, if you take the slope, this much only is the strain rate. Here strain rate is more increased. Here also strain rate is increasing for a particular time. If you choose a particular time interval, strain rate means the gap, that difference between, if you draw horizontal, then you can measure the strain rate here. That difference will be higher if you go upward. Okay, so instantaneous strain increases. Second one, strain rate delta E and delta T increases. This means the slope is increasing. So if delta E and delta T both are increasing, means that means slope of the curve is increasing. And time of rupture decreases. See, at this here the time of rupture is this one, this much time is available, but here the time of rupture is corresponding to this time. That means time is decreasing. So all these things are happening because of the temperature and strain. Now we have to define threshold creep. Threshold creep means the combination of stress level and temperature at which the strain remains constant at the instantaneous strain level is known as threshold creep. So at a threshold creep is actually defined for a particular combination of temperature and stress. For different temperature and different stress, the threshold creep will be different. So for a particular stress level and temperature, threshold is defined as a strain portion where the strain remains constant at instantaneous strain level. So within this curve, there will be a particular region where the strain remains constant. You can see here the strain remains constant means this line has to be horizontal. But for all these curves, there is no horizontal portion, but still you can identify a small portion within the curve where the curve will be almost horizontal. That means strain remains constant. So that particular portion is known as the threshold for creep. Okay, so that is the definition. It is there in your syllabus, that's why it is included in the presentation. Now coming to the next topic, that is prevention against creep. So all these points discussed here is actually contributing for the prevention of the creep. That is what is happening. Okay, so material with high thermal stability and high melting point. Of course, we have seen creep is directly depending on the melting point. If the temperature at which the stress applied is less than 0.4 times Tm, then the possibility for the creep formation is much less. So that creep formation temperature, if the temperature prevailing is less than 0. Tm, so it is depending on the melting point of the temperature. So a material having much higher melting temperature in Kelvin will have higher resistance for the creep. Okay, for example, ആയിട്ട് ഇപ്പോൾ 1000 മെൽറ്റിംഗ് പോയിൻറ്റ് ടെമ്പറേച്ചർ എന്ന് വിചാരിക്കുക കെൽവിനിൽ. അപ്പോൾ അതിൻ്റെ 0.4 400 കെൽവിനിൽ താഴെയുള്ളൊരു ടെമ്പറേച്ചറിലാണ് മെറ്റീരിയൽ ഉള്ളതെങ്കിൽ അതിന് ക്രീപ്പ് അധികം ഉണ്ടാവില്ല. അപ്പോൾ നേരെ വെച്ചാൽ 500-ലുള്ളതാണെങ്കിൽ 0.4 Tm എന്ന് പറയുമ്പോൾ എത്രയാണ്, 200 കെൽവിനാണ്. അപ്പോൾ 200 കെൽവിൻ എന്നൊക്കെ പറയുമ്പോൾ ചെറിയ ടെമ്പറേച്ചറാണ്. പക്ഷേ ആ ചെറിയ അതിന് കൂടുതലാകുമ്പോൾ തന്നെ എന്താകും, ക്രീപ്പ് നടക്കും. നോർമലി ചില മെറ്റീരിയൽസ് റൂം ടെമ്പറേച്ചറിൽ തന്നെ ക്രീപ്പ് ഫോം ചെയ്യാൻ സാധ്യതയുണ്ട്. ചില മെറ്റീരിയൽ എന്താണ് ഹയർ ടെമ്പറേച്ചറിൽ മാത്രമേ ക്രീപ്പ് ഫോം ചെയ്യൂ. സോ ഇറ്റ് ഈസ് ഡിപ്പെൻഡിങ് ഓൺ ദി മെൽറ്റിംഗ് ടെമ്പറേച്ചർ. സോ ഹയർ ദ മെൽറ്റിംഗ് ടെമ്പറേച്ചർ, more will be the resistance to creep. So all the material which is having high melting point will have resistance to creep. So if you want to prevent the creep, we have to use the material with higher melting point. Another thing is material with high thermal stability. The material which is having high thermal stability have better creep resistance. For example, an annealed material having high thermal stability is more creep resistant than a quenched material with low thermal stability. So if you want to resist the creep while designing a material, if you want to use a creep resistant material, then we will go for the annealed material rather than going for a quenched material, because annealed material is having more thermal stability than the quenched material. Thermal stability, if the thermal stability is more, that means more resistance to the creep. So alloys of high melting, see usually the alloys will have high melting point. Alloys of high melting point material like refractory alloys, super alloys and ceramics have excellent creep resistance. So if you want to prevent the creep, then use the material of having high thermal stability as well as high melting point, that will resist the creep. Second one is coarse grained material. Use of coarse grained material. By using coarse grained material, we can prevent the creep formation. Fine grained materials have higher mechanical properties at low temperature. See, higher mechanical properties, more ductility and all. So usually the while studying the TTD diagram, we have seen this one. Fine grained material have more mechanical property. So with low stress, they will deform more. That means if it is fine grained, it is indirectly favoring for the creep formation. So if you want to resist the creep, then it is better to use coarse grained material. However, coarse grain have better creep resistance to become at high temperatures. The grain boundaries are weaker than the grain index. So another thing we can do to prevent creep is to use the coarse grained material rather than the fine grained material. Similarly, dendritic grains are preferred over equiaxial grains. See, you might have studied about the structures of the different materials. So, dendritic grains are preferred over equiaxial grains application involving creep. So, if the material is having dendritic grains, then it will resist the creep much better than equiaxial grains. Single crystal alloys have excellent creep resistance. Directionally solidified alloys with columnar grains show high creep resistance. All these materials are having properties to resist the creep. So using such materials will we can prevent the creep formation, creep fracture. Now next thing we can do is precipitation hardened alloys. Of course, we have seen that if hard precipitated materials are there within the material, then dislocation movement is restricted. So that means we can resist the creep also. Fine insoluble precipitates prevent dislocation motion and grain boundary sliding, and such alloys are more creep resistant. So the material, if you want to resist the creep, then we can make the metal as precipitated and hardened alloys, adding some other elements and make it as precipitated and hardened alloys. Then it will resist creep much better than pure form. Okay. Now dispersion hardened alloys. This we have already seen. So fine hard insoluble particles uniformly distributed in the matrix material enhance creep resistance by resting movement of the grain boundaries. See here also by dispersion hardened dispersion allowing a material with dispersion material with another atoms in the dispersed form will make them alloys harden. That means the motion of the dislocation is restricted, hence we can resist the creep. Now the last one is substitution salt solution alloys. Here instead of dispersion hardening, we will be using substitution salt solutions. We will be substituting the parent metal atom with some other same uh, sized atoms of another material, which will do the same thing. That is, it will be restricting the movement of the dislocation. These alloys exhibit improved creep resistance since solute atoms introduce lattice strains which hinder the dislocation movement. Okay, here because of the introduction of the substitution solid atom, what happens is in the parent metal some strains are introduced wherever the substitution atoms are added. So this strain field developed will restrict the motion of the dislocation. So once the dislocation motion is restricted, that means uh, deformation is restricted. See if deformation is there, then only creep will take place. Okay. Now coming to the last topic, that is superplasticity. Superplasticity means deformation. We know that all the material will, some materials will not deform at all. That is what is called brittle. Some materials will have slight deformation, and some are having much higher deformation. So the materials which have very high deformation properties are usually known as superplasticity. See, they will even though they are metal, they will behave something like liquid like properties. They will show liquid like properties. That is what is known as superplasticity. So the advantage of having superplasticity is we can mold that metal into any shape, required shape, by applying the, of course, by applying the high temperature. These properties are usually exhibited at high temperatures. At low temperature, they will be very hard and having high strength, everything. So if you want to deform it into different shapes, then of course lot of mechanical manufacturing process are available, but still with less force and less effort we can fabricate much complicated shapes and all. That is the importance of super plasticity. So by adding some elements to a particular material, they can be brought to the superplasticity stage. So superplasticity refers to the ability of some material to deform extensively. See, ability to deform extensively as much as 20,000 2,000 sorry, not 20,000, 2,000%. അതായത് അതിൻ്റെ ഡിഫോർമേഷൻ്റെ ഈ 2000 മടങ്ങ് ഇരട്ടിയോളം അതിനെ ഡിഫോം ചെയ്യാം. ദാറ്റ് ഈസ് വാട്ട് ഇസ് ദ മീനിങ് ഓഫ് സൂപ്പർ പ്ലാസ്റ്റിസിറ്റി അറ്റ് എലിവേറ്റഡ് ടെമ്പറേച്ചേഴ്സ് ആൻഡ് സ്ലോ സ്ട്രെയിൻ റേറ്റ്സ്. സോ ദ ഫോളോയിങ് കണ്ടീഷൻസ് ആർ ടു ബി സാറ്റിസ്ഫൈഡ് ഫോർ ഒബ്റ്റൈനിങ് സൂപ്പർ പ്ലാസ്റ്റിസിറ്റി. ഒരു മെറ്റീരിയൽ സൂപ്പർ പ്ലാസ്റ്റിസിറ്റി ബിഹേവിയർ കാണിക്കണമെങ്കിൽ ഇത്രയും സാധനങ്ങൾ സാറ്റിസ്ഫൈ ആണ്. ഫസ്റ്റ് വൺ ഈസ് വെരി ഫൈൻ ഗ്രെയിൻ സൈസ്. ദ മെറ്റീരിയൽ ഷുഡ് ബി ഓഫ് വെരി ഫൈൻ ഗ്രെയിൻ സൈസ്, ദാറ്റ് ഈസ് 510 micrometer ഷുഡ് ബി ദ grain size. High strain rate sensitivity, high temperature, that is it will show superplasticity only above 0.5 tm, and low strain rate 0.01 to 0.001 length deformation per second, that is the strain rate. So strain is actually unitless, change in length by original length, that is the strain. So per second only this much deformation should be there. So that means it is deforming very gradually, but it can be deformed to a much greater extent. See, 2000% increment in original length is possible by this material. In addition, presence of second phase which inhibit grain growth is preferred. Most super plastic alloys are of eutectic or eutectoid composition. So sometimes if you see what happens in a material is, if you heat the material to a particular temperature, then recrystallization and all will take place, which will restructuring and even regrain, the grain refinement, everything will be taking place, which will have a which will act as a which will inhibit the deformation properties. That is what is actually happening. So presence of such second phase which inhibit grain growth is preferred for the superplastic. In addition, presence of second phase which inhibits. So by heating, some second phases are formed within this material which will actually inhibit the grain growth. If the grain growth is favored or grain growth is happening, then recrystallization, everything will take place and the material will go back to its initial structure and properties. So that is not, if you inhibit that one, then it is possible to have superplasticity. Deformation mechanisms like grain boundary sliding and grain boundary diffusion, which are operative at elevated temperature, are reported to be responsible for the superplasticity. Because of these things, that is grain boundary sliding and grain boundary diffusion, mainly the superplasticity is achieved. Actually, it's a extended version of the creep, we can say. Now coming to the application of superplasticity. Superplastic phenomenon is widely employed in metal forming processes like thermoforming, blow forming, vacuum forming, deep drawing, etc. In all these processes we are using superplasticity property. See, large, deep and complex shapes can be made in one piece in a single operation. See, that is the importance of this one. With the superplasticity, large, deep and complex shapes can be made in one piece in a single operation, of course with lesser energy and lesser force. Another option manufacturing process which we can use to form the complex shapes is casting and all, but it is costly as well as energy consuming. Of course, higher force is required. Here, since it is deformed to any shape, just like it behaves like liquid in property when it is heated to a particular temperature. Of course, it is a solid state, but still it will have all the property like a liquid. We can നമുക്ക് ജസ്റ്റ് ചെറിയൊരു ഫോഴ്സ് കൊടുത്താൽ അതിനെ എങ്ങനെ വേണമെങ്കിൽ ഡിഫോം ചെയ്ത് കൊണ്ടുപോകാം. അതാണ് അതിൻ്റെ പ്രത്യേകത. സോ കോംപ്ലക്സ് ഷേപ്സ് ക്യാൻ ബി made. Usually it is used in forming process, forming, drawing forming എന്നൊക്കെ കേട്ടില്ല. ഫോമിംഗ് എന്നൊക്കെ വെച്ച് കഴിഞ്ഞാൽ നമ്മളൊരു ഭാഗത്ത് നിന്ന് ഒരു പ്രത്യേക ഡൈ ഉണ്ടാവും. ഡൈയിൽ ഏത് ഷേപ്പിലുള്ള മെറ്റൽ ഷേപ്പാണോ വേണ്ടത് അതിൻ്റെ ഡൈ ഉണ്ടാവും. അപ്പോൾ മെറ്റൽ നമ്മളിപ്പോൾ എന്ത് ചെയ്യും, ഫോഴ്സ് ചെയ്തിട്ട് അതിൻ്റെ ഉള്ളിലേക്ക് പ്രസ് ചെയ്ത് കയറ്റി. മോൾട്ടൺ നോർമലി നമ്മളൊരു നല്ലോണം ചൂടാക്കിയിട്ട് ഓൾമോസ്റ്റ് മോൾട്ടൺ സ്റ്റേറ്റിൽ തന്നെ പ്രസ് ചെയ്തിട്ട് ആ ഷേപ്പിൽ ഫില്ല് ചെയ്യിക്കുകയാണ് ചെയ്യുക. അതാണ് ഫോമിങ്. ഡ്രോയിങ് എന്ന് പറഞ്ഞാൽ അപ്പുറത്തെ ഭാഗത്ത് നിന്ന് വലിച്ചെടുക്കുകയാണ് ചെയ്യുക. ഒരു ഭാഗത്ത് നിന്ന് ഡ്രൈൻ്റെ ഉള്ളിലൂടെ വലിച്ചെടുക്കും. അപ്പോൾ ആ ഷേപ്പിലേക്ക് വരും. വലിയ റോഡിൽ നിന്ന് ചെറിയ റോഡൊക്കെ ആക്കി എടുക്കണമെങ്കിൽ നമ്മൾ ഡ്രോയിങ് പ്രോസസ്സാണ് യൂസ് ചെയ്യുക. അതായത് ആ ഒരു ചെറിയ കാവിറ്റിലൂടെ കടന്നു വരുമ്പോൾ അതിൻ്റെ ഡയമീറ്ററിലേക്കുള്ള കമ്പീൻ്റെ ആ ഒരു റോഡായിട്ട് മാറും. വലിയ ബില്ലറ്റിൽ നിന്ന് ചെറിയ റോഡാക്കി എടുക്കാൻ പറ്റും. അങ്ങനത്തെയൊക്കെയാണ് ഡ്രോയിങ് എന്നൊക്കെ പറയുന്നത്. അത്തരം പ്രോസസ്സ് നമുക്ക് എളുപ്പത്തിൽ ചെയ്യാൻ പറ്റും. അധികം ഫോഴ്സും കാര്യങ്ങളൊന്നും വേണ്ട, അധികം ചൂടാക്കുമ്പോൾ. In force requirement are also significantly lower due to reduced flow stress. In thermoforming, sheets are made to conform to a heated die by application of vacuum or pneumatic force. So in thermoforming, what we will do is we will be sheets are made to conform to heated die. So heated die will be there. Into that we will be uh, just pushing this material into that die by application of vacuum or pneumatic force. Production of aerofoils in gas turbine is an important application of superplasticity. One of the main component which is produced by using superplasticity principle is aerofoils in gas turbine. These are all the applications of superplasticity. Okay, thank you.